All right, hello everyone. My name is Nader Famili, and I represent JMA Wireless. JMA is a company that works on connectivity infrastructure. So not so much on the IoT devices or applications. So my talk would be basically about the options for infrastructure for IoT. And then I would have some use cases based on the actual deployments that we've had across US. So this talk will not be very deep academic talk as our other friends have done. So you can just sit back, relax, and enjoy. All right, basically just one slide about our company, so you become more familiar with us. We're a company that provides end-to-end solutions for the wireless industry. As far as the macro networks are concerned, we provide them antennas, connectors, jumpers, cables, and also more recently carrier-based baseband solutions. In terms of private wireless, ever since it has become a hot topic in the last few years, we have been in the forefront of that, designing multi-carrier private networks with virtual RAN, and I will be discussing more about that later on. And one of the biggest portions of our business is our DAS, distributed antenna systems, that a large portion of the DAS installations across US is from our company. So let's move on to categories, different categories of IoT. You are very familiar with that. And if you refer to 10 different white papers, you will see 10 different categorization of IoT. So I try to stay within a more generic categorization. We do have the massive IoTs. These are the little things on meters and sensors and trackers. So there's quite a bit of them. When we talk about billions and billions, this is the category we're talking about. They are meant to be low cost and narrow bandwidth because they send very infrequently information or receive information packets. They will primarily rely on battery power, obviously because they're small, they cannot be connected to a power source or have a power supply. And because a lot of these things are used in on things that are not very open, you know, the electrical or mechanical things that if they're in a building, they're in the basements, or if they're in industry, they're tucked away in some place where coverage is very hard to get. So this type of devices, they need deep and wide area coverage. And why wide area? Because they would be scattered all over the cities and rural areas as well. These devices are usually not very delay sensitive. You know, there may be exceptions, but typically they are not delay sensitive. Once in a while they send something, and once in a while, a couple of times a day, they may receive information. The second category are the broadband IoTs. These are the things that you would have in your personal or commercial vehicles, trains, autonomous vehicles, wearables, or AR or VR. Because of their usage, they would need higher data rates and very frequent communication between them and the system. They need excellent coverage in the sense that you will not get high data rates unless your coverage signal to noise ratio is very high. They would need wide area or focused area coverage. That depends on the application. If you have an autonomous vehicle, for example, you obviously want to have very wide area coverage. Or if you have AR, VR, they may be confined to the walls of a building. Some of the applications may fall into URLC application and have delay sensitivity, and some may not. That again depends on the type of And the third category, which is industrial IoT, and that's very similar to critical IoT. These are used in manufacturing, mining, utilities, basically all the big plants. The characteristics of this type is that you would have integration of wireless with wireline, Ethernet, and time-sensitive networking, which is very common in manufacturing. It's based on 802.1 IEEE standard. And as the name implies, it's very sensitive with respect to time and requires synchronization pretty much on all the nodes. And then we have the URLC applications that usually require a lot of high reliability and very low latency. These are specifically in manufacturing, very important in manufacturing. Low latency of 1 millisecond. In fact, this was a number that was put forth by the manufacturing lobby. And in fact, they wanted something less than that. But that's what we ended up with in 5G. The common platforms, and these are the most common platforms that are available for IoT, but this is by no means exhaustive. There are other things as well, but this constitutes the bulk of the platforms. Obviously, we always start with the RAN, your favorite commercial operator, T-Mobile, AT&T, and Verizon. They provide very wide area coverage across the US, and they generally provide very good throughput outdoors and very near indoors. And obviously, as you go deeper into indoors, then the performance degrades. They paid tens of billions of dollars to buy spectrum, so they have lots of spectrum. Right now, they all have more than 300 megahertz after the C band and the C+ band is being cleared. And they would use that to good use by carrier integration. So you could expect very high throughputs from your commercial carrier. Now, because they are the main horsepower for the wide area coverage, they also need to provide very deep coverage for our IoT applications. Now, coverage enhancement was one of the techniques that was developed called CE, Class A and Class B, where basically the signal is the information is repeated a few times or hundreds of times or even thousands of times. And that helps very much in terms of the link budget. And by doing that, they could reach the IoT devices that are really tucked within some corner of a basement or something. Obviously, as you do that, you're eating into the resources of your channel, and your throughput overall degrades. But if you have a channel in an area where you have a lot of industrial sensors, you may want to dedicate a channel to that and do coverage enhancement. 5G provides better latency than 4G, but it's still not coming close to the promised 1 millisecond. If you look at the 4G right now, the promise was anything from 10 to 20 milliseconds, but in reality, the systems are more in the 40 milliseconds range. And when it comes to 5G, again, the promise is 1 millisecond, but based on my own experience and anecdotal, right now the systems are closer to 10 milliseconds. Now, obviously, they will improve, but I doubt they will reach that number anytime soon. The second category is DAS. That's for the ones who are not familiar. That's the systems that extend the coverage from the RAN into indoor venues or any places where the coverage is not very good. That is very common in large facilities such as airports, stadiums, and casinos, and whatnot, convention centers. I put a note here with regard to analog DAS, because analog DAS, and I would discuss it a little bit more later on, unlike the digital DAS, really offers very low latency, and it could be used for the URLLC applications, IoT applications, whereas the digital DAS may not be suitable. Private networks are, again, a very important platform for your IoT, because the enterprise that is using that has total control over its coverage and capacity and latency and security. And it is because it is independent from the public networks, and it's really controlled by the enterprise itself. And that is, as I mentioned earlier, it is hard to rely on the commercial networks if your expectation in terms of latency is very low, and also reliability. So you might as well have your own private network. Wi-Fi is very pervasive and very cost effective. With Wi-Fi 6 and 6E, we have, with 6E, we have like close to 1.2 gigahertz of spectrum. So you can expect a very high throughput. However, in terms of performance, in terms of reliability and mobility, those are the things that may not be very competitive with the 3GPP standards. And of course, all of these types of platforms will find their niche in the system, in the marketplace, based on the requirements of the marketplace and their capabilities. Last but not least are the non-3GPP LPWAs, low power wide area. Those are the LoRaWAN and Sigfox and so on. They are really meant for devices that really they need maybe a few bits per second or something, and they provide very minimum power in terms of output and input. A very small packets of information. Again, there are other types. There's ZigBee. There's satellite-based IoT platforms. Or I'm not going to talk about that now, because my company JMA Wireless really focused on DAS and private network. From now on, those are the things that I'll be talking about, and our examples are also pulled from those type of platforms. Distributed antenna systems. This is a architecture that is very common among the DAS vendors, where you have a head end, which basically is working with the OEM base station. It's really taking the signal and it does RF conditioning of the signal in terms of filtering or amplitude, and then it does whatever combination and splitting that it needs to do, and then it converts the RF into optical signal and sends it to the remotes. In addition to those functionalities, the monitoring of the system is also residing within the head end. These are usually modular, very nice and neat. In our systems, for example, we have modules that can accommodate very high power base stations as well as low power base stations. Our optical conversion is analog. We're not using digital, which some of the vendors are using. Each one has its own merit. The analog has extremely wide band and also extremely low latency. The digital does not have as wide band as analog, and it doesn't have and has latency issues because there's an inbuilt latency when it comes to processing of the signal and digitizing it. However, it offered other benefits. The remote is meant to convert the signal back to RF from optical and amplify it and distribute it among the intended coverage area using the passive coaxial network and the passive DAS antennas. Private wireless solutions have been around. The topic has been around for a few decades, at least in the last 30 years or so that I've been in the industry. But it has never been a very hot topic until recently. And the problem has always been that the need was always there. So very big enterprises always wanted to have their own network, so they wouldn't be beholden to the commercial system, both in terms of reliability and in terms of availability of coverage. And those are the things that they wanted to make their own decisions, but they had to be relying on the commercial network. So there always was a need for it, but there were never really serious solutions because there were never really a spectrum dedicated to that. And that all changed with I think 2015, with CBRS was approved from 3550 to 35.7 megahertz was allocated to basically shared spectrum for this purpose. Our solution for the CBRS private network is one that is based on the MOCN architecture, which is multi-operator core network. As you can see, our system can accommodate multiple cores from multiple operators or whatever other entities that want to use the CBRS. They could be sitting on the cloud or they could be on the premises. Our baseband system itself called XRAN. Our XRAN is a fully software unit. Means it's just a piece of software. It can sit on any off-the-shelf server and your regular Dell server, and that's why it offers. That is unique in the industry actually, because other solutions usually use a combination of software and hardware, and their hardwares are usually accelerators to do FFT and inverse FFTs faster. But we do inverse FFT and FFT in software, so which is very unique. The benefit for that is that, as you can see, the upgrades in this industry happens all the time, and for us, it's just upgrading the software, just downloading another software. But for people who have hardware components to their solution unfortunately need to be visited, and things need to be removed and replaced. And if you're talking about large scale with thousands and thousands of customers, that becomes a very big deal. Right now, we can do up to 800 megahertz per server of connectivity capacity. We do have our remotes, we have different kinds. We have indoor remotes, outdoor remotes, and they basically the same infrastructure works for both of them. The spectrum that is available could be doled up in a simulcast or in a sectorized way, depending on how much spectrum is available and how many cores are connected and what is the coverage intention of each of those participants. This is the same basic thing, except that the focus here is on the applications. As you can see, the private network is the multi-core, multi-operator core network. Can accommodate many different use cases. You can have your mobile networks. You can have your cameras, which is basically IoT. You can have push-to-talk for security. You can have another application that we found out to be very popular and we didn't actually anticipated in the beginning was the fact that the CBRS is being more and more used as a backhaul for Wi-Fi. Because before, if you had to put a Wi-Fi access point somewhere, you needed two things. You needed power and you needed Ethernet cabling. Or there could be PoE, but still you needed the cable. The cable wasn't always easy to pull and wasn't always cheap. Imagine, for example, a parking lot where they have to dig through the parking lot to lay the cable to put the access point somewhere. But if they can use the CBRS as a backhaul, all they need is power, and you have power available in a parking lot on the lights and stuff. So that makes things a lot easier. Cell to video, cell to Ethernet, cell to machine. Those are the things that maybe I will talk about a little later. But basically, amalgamation of all different applications, whether they be human to human, human to machine, or machine to machine. And this is very important because what we found out very early on was that our customers in the DAS business and our customers on private network business are a lot of times very much the same people. Means these are the verticals that have a lot of need and have a lot of money. Your typical hospitality, medical, sports, entertainment, and they both need, they all need both of them. Now, our solution, because it allows a lot of nodes of these systems to be common, basically, and the passive network portion could be common. So it basically means that if you have a JMA DAS system, which a lot of people have in those verticals that I mentioned, and they could easily add the private network to that with up to 80% reduction of cost, and really within days, not months, as some others would have to do. So the fact that we can combine these two provides a unique opportunity for customers to enjoy the benefits of both, and I will show some examples of that later. Now let's talk about some deployments that we've had and some use cases. Starting with the hospitality, these are we have provided many of these systems, several of them in Vegas, casinos and hotels in Vegas. So I don't know if I'm allowed to name names, but I'm just going to say the famous ones in Vegas. Basically, we provide them with both DAS and private wireless, and they can use that for two things. They can use that for their own operations, or they can use that for their guests and some services that they offer in the rooms. If you look at the front of the house, our DAS really is catering to the needs of the guests with their cell phones. And mind you that before we installed these DAS, the coverage was very poor. So you would think that the coverage would be very good there, but that wasn't the case. That was very poor. So DAS was very much a welcome thing, and people can now enjoy the smartphones and the voice and data and use their preferred carriers. Now, the private network in the front of the house is really used for operations. And a lot of the people, if you've seen them, they have handheld devices, and those need security because a lot of them are point of sale devices, and they need reliability. They need to work at all times in all places, and just basically the comfort of being wireless, and they can take the devices anywhere. In addition to that, the IoT becomes very important because when you talk about casinos, you're talking about really hundreds and hundreds of electronics gadgets that are scattered around this venue, and a whole lot of them would have sensors and meters and whatnot. When going back to the back of the house, where maybe ordinary people are not allowed to be there. The private networks takes center stage in terms of the operation. But the fact that our multi-operator, our network, a private network, is a multi-operator system, what it basically means is that if you have a phone with dual SIM, which pretty much after, I think, iPhone 11, every phone has a dual SIM capability, whether it's 2 hard SIMs or one hard, one soft SIM. The users of the devices can easily use the private network and the commercial network at the same time with the same device. So that gives them the added advantage of having connectivity at all times. These are some of the in-room services that, and most of this has already been deployed. So these are not theoretical, these are things that have been done: keyless entry, a wireless thermostat. One of the operators has worked with us, and we have provided CBRS based TVs, where basically they stream their videos through CBRS, and other things such as automated room service. When you go outside, again, the private network is very important for people. Again, with the devices, the wireless devices, and a lot of them are point of sale devices, as I mentioned earlier. So security becomes very important because you're dealing with people's credit cards, and you obviously don't want that to be hijacked by any hackers. Going to another vertical, very important vertical for us is education, and mostly universities. We have worked with multiple universities, but right now, the one that is most mature and deployed in greater scale is Syracuse University. Our private network in the universities is very important for them because with the digital age, they want all their staff, all the students have constant access to the information is available in the libraries and on the servers and whatnot. Security is very important. Unfortunately, we've had some incidents a few days before with a couple of universities. Operation of the universities across their campus and closed-loop AI systems that has been deployed on these systems. Immersive learning, again, is another aspect that is becoming more and more important for universities. So now they don't have to be in a specific center to be enjoying that. They could be, the student could be sitting in their rooms and in their dorms and doing the VR, for example. Some of the IoT applications that we have deployed are location beacons and keyless entry to dorms and a few other things. Like it or not, athletics is a big part of major universities, and they really like to do deep real-time athletic analytics when the game is going on. When the game is going on, they want to have some immersive fan experiences. Those are the things that we have provided to Syracuse universities and others. Advanced field communication. Right now, our private network systems are being used in all NFL systems. So when you watch NFL and you see all the coaches talking to the quarterbacks and referees talking to each other, they're all using our system. And it's very much secure, very much reliable, and they're very happy about it, as far as we know. So another set of applications that I like to talk about are the warehouses. We have a very, very large collaboration with Department of Defense when it comes to warehouses and smart warehouses. The use cases of smart warehouses are numerous, really, because it causes the reduction of cost, and because less labor, less inventory to worrying about, shipping becomes more streamlined, improved efficiency in terms of productivity and the lead time, and improved accuracy, obviously, as the human errors would be minimized, and increased throughput as the speed of how things are stored and shipped and processed while they're there improves. How do we achieve that? We achieve that through persistent connection and synchronized connection, very reliable connections, wireless connections, and persistent, meaning that they're always there with high accuracy, high efficiency, and high security. And we are empowering automation in every aspect of the smart warehouse. The model that we have used so far are this type of architecture, basically, which is a public and private infrastructure. Again, DAS plus the private network, and the public and the private network is using the off-the-shelf IT infrastructure that in many cases already exists. We have used both FR1 and FR2 spectrum. For the ones not familiar with that, FR1 is, I think, below 6 gig, whatever, the lower spectrum that are commercially on your cell phone, and FR2 are the millimeter wave spectrum. Why that is important? Because I'll discuss it a little later, but the FR2 really provides the ultra-high throughputs that are needed in some aspects of the operation. Then if FR1 provides the wider coverage and very fast communication as well in some aspects. It is highly scalable, obviously. We can reduce or increase. And again, the very powerful aspect of this is that the same infrastructure is used for mobility, for human to human, human to machine, machine to machine. So we don't have to pull different kind of cables and put different antennas for different things on infrastructure. Does it all. You see the name Deloitte because Deloitte is basically the major integrator that pulls all the IoT applications, not just IoT, IoT and other types of applications and devices and all the things that are sitting on the infrastructure that we provide. This is another example of another location for Department of Defense that we have installed. I think it's in Yorktown, if I'm not mistaken. And robotic automation, optimization of the warehouse, and 5G for perpetual inventory audits and whatnot. These are the things that, again, we are doing right now. And in the very, very harsh and very, very demanding environment of Department of Defense warehouses. Open RAN is outside the realm of this discussion, but I just needed to put it in there because the following examples use Open RAN access networks. Open RAN access networks, or ORAN, are basically an attempt to make the telecommunication industry go from a vertical model where one vendor provides everything, all the software and hardware, to a horizontal model that we have in IT, for example, where different vendors provide different nodes of that system, whether it's software or hardware. Obviously, when it comes to that, they need to be highly interoperable, and they need to be standardized, and the software that's managing the whole thing needs to be open, so people know what they're doing. And this is a big wave in industry. How far does it go? I don't know, but we do have solutions based on open and access networks and these examples. This is again another Department of Defense facility where we're providing coverage to both outdoor and indoor, and we're using again both commercial frequencies as well as private network. And as you can see, as the ones who are familiar with ORAN architecture, we have the central unit and distributor unit, and the front hall is using a 7.2x ORAN architecture. We can't really obviously talk about the details of this. This is all military, but just the bullet points are rapid data analysis, digital inspection, ground support, connected maintainer, remote engineering support. Basically, a wide coverage area, indoor and outdoor. People need to have access to data immediately and securely and reliably, and they need to send data back immediately, reliably, and securely. And this is what we are providing. This is an example of the coverage in one of the hangars, I think a couple of hangars. This is a CBRS coverage, and I have a thumbs up, meaning I have 5 minutes, I think. Anyway, the coverage is green, which means it's very nice. The blue stuff are the airplanes. Inside the airplanes, obviously, is not as good. It's all metallic thing. The signal doesn't go in there very well. But it's still blue, which means that it's still good enough to make, for example, a phone call, but not good enough to do any high throughput application. Hangars are a very important part of the operation because a lot of the activities in terms of testing and overhaul and maintenance happens in the hangars, and they need to have excellent coverage for that. Outside, the refueling area is also very important because, again, a lot of activities happens there. As you can see on the left side, we have low band 600 megahertz. This is making sure that the push-to-talk radios work everywhere, and they do. And you can see the coverage either red, which is excellent, green, which is very good, or purple, which is good enough. When you go to the right side, it's your CBRS coverage, which is again for the refueling area, where it's the intended area, is very good. Right around it is still good enough, and outside that is not good, but who cares? Nobody goes there for high throughput activities. 5G logistics, again, another example of an area where you have lots and lots of stackable racks, very narrow alleyways. So you can't rely on the signal from outside to do anything. It won't do anything. So you need to install your own private network, and in addition to that, you need to have extremely high reliability and security, being a military installation. And a lot of these, they have sensors on them and meters, and so lots of IoT devices that would be strewn about in this area. I think I just have 2 more slides, so let me just talk about this one. This one is logistics area for the Department of Defense. DLA is just a defense logistics agency because they have their own standards for logistics. But what's interesting about this area is it's very complicated because it's not just wireless, it's wireline, it's EDI. EDI is like electronic data interchange, and some sort of data interchange. So they have all different types of things going on. A wireless system needs to be, again, very highly reliable to be able to work with these systems, which are wireline, so inherently more stable and reliable. And the last example I have is from a facility that belongs to the Marine Corps. This is a very interesting place. I wish I had a video of that. I do have a video, but I wish I could play that. But this is where you have basically a matrix of bins, really very large matrices, and we are just showing a very small portion of that. Hundreds by hundreds of bins, and you have all these robots that very, very fast, they go to the bin that they're supposed to go, and they dump their stuff or pick up stuff, and then very, very fast move away. So here you really need very high reliability, very low latency, and obviously high security for all the defense stuff. This is all I have. I hope you've enjoyed it, and let me know if there are any questions.